All right. Have you guys run into any questions or anything you've got up till now?
Um,
No,
I guess we've been talking about water moon. What did you guys think of that video? That was pretty sweet, huh?
yeah,
it was.
I think every soils student that ever existed should have to watch that video because it's like an all-time. It's great, really, because it's so visual and you can kind of see how water moves through soil and stuff. So yeah, it's one of my favorites. In fact, a few years ago, I was trying to find it and like I couldn't find it on YouTube. And so I contacted WSU and they sold me like a DVD of that video and it cost me like $70. And now it's like it's on YouTube, so we can watch it for free. So yeah, did you guys have any questions about any of that stuff?
um, I had a question about like the drainage and stuff.
Hmm.
So when it comes down to depending on your soil type, that's what how much drainage you're gonna get through your natural soil and stuff.
Yeah, I mean it's really related to texture. That's a big player. It also has to do with soil structure too, right? Because if we've got that platy structure,
Gonna
things
stick
aren't going to
around.
drain very well. So, around here we've got really sandy soils,
Mhm.
and if you look on like those the soil web survey that we did,
Yeah.
it usually describes our soils as like excessively drained.
Hmm.
That means that they drain or
Drain
water
really quick.
percolates through 'em really fast.
Yeah.
And that's a function of that, mostly of the texture, but also the structure. You know, organic matter is a player in it too, because it kind of creates those bigger macro pores
Yeah.
and water can move through those quite easily. So, yeah, good question. Anything else? Manish, did you have anything?
No,
No.
nothing.
Okay. All right. Let me share my screen here and we'll get going. That looking good?
Yeah.
Okay. We're going to talk about clays and colloids, clay mineralogy. Okay. We already know what clays are, right? Those are the less than 0.002 particles. So they're microscopic. And a colloid. So that's probably a new word for you, but what a colloid is it's basically the reactive portion of the soil. And that can include clays because clays are reactive, but it can also include organic matter. Organic matter is reactive as well. So those two things, organic matter and clay particles, are kind of lumped into this thing that we call colloids. Now, the way we get to clays is everything starts out as a rock, right? And then over time, they're just the natural product of weathering and mineral breakdown. Okay. They tend to have crystalline structures, and I'll show you what that means in just a little bit. And they actually end up forming sheets. So if you look at this, this is a scanning electron micrograph of a clay particle. You can kind of see this sheet arrangement, how they're kind of stacked on top of each other. And what it does is it forms a silica tetrahedra and an aluminum octahedra. And we'll talk about that again in just a minute. But this is 10 micrometers. So a billionth of a meter. That's 1,000, 10. No, what's 1,000 times 1,000? That's like 10,000, isn't it?
Yeah.
I'm not very good at doing math.
And how do you say those? Was at the bottom? Si or
Silica. That's the element
Oh,
silicon.
okay. Okay, yeah.
Yeah,
Okay.
yeah. So no, that is a million. It's a millionth of a meter. So imagine,
That's a lot.
yeah, dissecting a uh, a meter into a million little bits. So yeah, very very tiny microscopic particles. Okay, now the building block of these sheets and these structures, the crystalline structure, is generally silicon, aluminum, oxygen, and then this OH, which is a hydroxyl. And notice these charges, these are kind of important. So oxygen's a -2, aluminum's a +3, and silicon's a +4. Okay, those are going to be kind of important as we go along here. Everyone, I like to watch Jeopardy, and every once in a while they'll ask what the most abundant elements are in the Earth's crust. I'm pretty sure that this is number 1 right here, oxygen. And this is not an element, this is a compound, so it doesn't count. But then I believe after that, we get into the silicon and aluminum. And then after that, it's probably into the iron and stuff like that. So very, very abundant. You'll often, if you guys spend a little bit of time in agriculture, you find a little bit of everything. And I ran into a guy a couple years ago that was selling silica as a soil additive.
I didn't know.
No.
Silica as a soil additive. And that's just ridiculous, right? Because the soil is made up of silica. What a bunch of crap. Okay. All right, let's look at a few of these different types of structures. So on the far left here, this is an example of a kaolinite. Okay, and we're going to go into detail what a kaolinite is. Number B, this is a fine-grained mica, so probably a 2-to-1 type clay. Here's a montmorillonite, which is also a 2-to-1 clay. And D is a fulvic acid or a humic acid. So this is actually organic matter right here. That's the broken down point. So again, all these are different colloids. They're clay particles in organic matter. And all these different structures have properties that make them reactive, the reactive part of the soil. Okay. You guys aren't old enough to have played Tetris ever, are you?
I played it before.
Okay. So cool. What's Tetris?
It's the puzzle game.
Yeah. How many blocks are in the puzzle?
I do not know that one, but I know it's like a puzzle game.
Okay. All of the building blocks of Tetris are made of 4 like squares stacked together, right?
Yeah.
And it could be like in an L shape or a square shape or a flat shape or one of those
Like
Z Z shape. Yeah. So remember that Tetris is made up of 4s, right? And in the soil, when we have a silica surrounded by oxygen, okay, so you can't see it here on this ball and stick diagram, but there's a central element right here, which is silicon. You can see it over here a little bit. But when you have a silicon that's surrounded by 1, 2, 3, 4 oxygens, it's going to form this shape right here. And so this shape is 4-sided. So there's a side here, 2 here, 1 on the back side that you can't see, and then 1 on the bottom that you can't see. And these are just like different physical ways to describe a tetrahedron. Okay, this is what we call a ball and stick figure. This is like a bubble figure, and then this is like a polyhedron type figure. It's all the same thing. For soils, I kind of like this one the most on the top because we can really see that sheet structure very well when we use this type of model. But yeah, does that make sense? Tetrahedron, 4 sides. So there's a side, this darker side here, 1 on the back side that you can't see, and then 1 on the bottom.
Yeah.
So it's forming this 4-sided figure. And silicon is the central element. Okay, so here we've got a silicon in the middle. We're going to surround that thing with 4 oxygens. And here you can see it a little bit better, right? The 4 sides.
Yeah.
1 facing you, 2, 3, and then 4 on the bottom. And what happens in the soil is you'll get an arrangement of these things. So here comes another one. And these guys will hook up and they're starting to form a sheet. Okay. So this is kind of the beginnings of a sheet. We've got several silicon tetrahedrons showing up. They're linked together and they form a sheet. Now, depending on the mineral, they're going to form different looking sheets. Okay. And that's what I wanted to show you here. So if we're looking at just like an isolated, you know, one silicon to 4 oxygen, this is the kind of shape that we're going to get. They can chain together like this, so they're like alternating. This is what we call pyroxenes. You guys don't need to remember any of this, other than they will arrange themselves in different shapes based on their parent materials and things like that. And this is kind of the framework at the very bottom down here. This is a quartz. So quartz is SiO4, which is this right here, SiO4. 1 silicon, 4 oxygen surrounding. Okay. The cool thing about some of these shapes is if you look down here, you see this hole basically, if you're looking at it from the top. In some of these minerals, that hole just happens to be the perfect size to fit in a potassium element. Okay, which plants need potassium to grow. And so if you get these mica type groups, a lot of the times they'll come with a lot of potassium, which the plants can use to grow, which is fantastic. Okay, let's look at the same thing. So the top of this is a ball and stick figure. This is the polyhedron type figure, and then the bubble figure down here. But again, we're looking at several of these tetrahedra that join up and are now forming a sheet. And if we look at this from the top, you see these cavities up here? These are 2-to-1 type materials, and they've got a nice space in here for a potassium. Okay, yeah. So this is the ball and stick figure looking at it from the top. This is the bubble figure looking at it from the top. And this is the polyhedron figure looking at it from the top. Do you guys know this? This is interesting as heck, isn't it?
Yeah.
That's right.
Mhm.
Okay. So silicon in association with oxygen forms a tetrahedron, so 4-sided shape. Now, aluminum, it'll also join up with oxygens, but we need to remember that it's a little bit different. So aluminum is going to form an octahedral sheet, an octahedral shape. Okay. So again, we've got this aluminum element here in the middle, atom, and it's surrounded by 1, 2, 3, 4, 5, 6 oxygens. And then if you put that into one of these polygon type shapes, how many sides do you guess that has?
Mm,
Eight sides.
Yeah, there we go. 8 sides.
this is
Octahedron.
this is aluminum with oxygen, you said? Or?
Yep. So aluminum here in the middle, and then oxygens out here on the sides. So yeah, if we were to look at this one, whoops, go back. 1, 2, 3. There's one we can't see here, 4, and then we get the same thing on the bottom. So an 8-sided shape. So same thing. We start out with an aluminum right here. We're going to surround it with 3 oxygens on one side, 3 oxygens on the other, and that forms our octahedral shape. Okay. And then we get a bunch of them come in, and we can have this octahedral shape that starts to form a sheet.
And they all have to have the 1 aluminum and the 7 oxygen.
Well, it actually ends up being, some of them get shared, right?
Yeah.
But if you were just looking at, if you were to divide this into one individual aluminum octahedral unit, it's going to have 6 oxygens surrounding it.
Okay.
Yeah. So for example, this one right here, it's got 1, 2, 3, 4, 5, 6, but you'll notice that it's sharing this oxygen up here
Yeah.
and this one over here with this other unit. So that's how it works out. If we look at the same thing again, bubble figure, this is the polyhedron, and then the ball and stick figure. So yeah, we got these cavities up here. Very interesting. We can also have a tri-octahedral sheet, but for the purposes of this class, we're not going to really focus on these too much. And gosh, it's been such a long time since I learned what a I can't even remember what they are. 1, 2, 3, 4, 5, 6. Yeah, don't worry about it. I think it's just how it's arranged, right? This
Yeah.
one's packed in really tightly, and this is packed in less tightly, so it ends up being a dioctahedral. This has got more aluminum elements per shape. Okay, so we talked about at the very beginning, there's different arrangements. Okay, we can, and when you see something that's described as a 1-to-1 or a 2-to-1 or a 2-to-1-to-1, this is always referring to the tetrahedral, the number of tetrahedral sheets to the number of octahedral sheets. So if we've got a 1-to-1, that means that there's one tetrahedral sheet that's in arrangement with one octahedral sheet. Okay, and I'll show you that in just a minute. We can have 2-to-1 where there's 2 tetrahedrals and 1 octahedral. And I want you guys to remember that when you have a 2-to-1, the octahedral sheet is always in the middle. So can I draw on here? Let me draw on here with a pen. So I always remember it like this. Have you guys ever seen Napoleon Dynamite?
Yeah.
And he says, "Give me your tots, man." Manish, do you know what tots are?
No, I don't.
They're tater tots. They're like a French fry, but they're in a little cube. You ever
Uh,
had those?
no.
Okay, your assignment is to go to the store
That's a
and
Okay.
find tater tots and buy them and eat them, because you'll never forget this. Okay,
Okay.
and you guys will remember that tots means that there's an octahedral sheet that's sandwiched between 2 tetrahedral sheets. Clear as mud?
Yep.
Okay. And we get different kinds, right? So let me go back to the laser pointer. So we can have 2-to-1 clays that are expanding. I've got a sweet video on this I'm going to show you in just a minute. And we've got 2-to-1s that are non-expanding. So if the big examples that I like to use in this class is a 1-to-1 clay is usually what we call a kaolinite. A 2-to-1 clay that does not expand is an illite. That's an I-L-L-I-T-E. And then a 2-to-1 that is expanding is what we call a smectite. Okay. Great. I need to turn this off. Okay, so let's look at how these are arranged. Okay, so this left hand side here is an arrangement of a 1-to-1. All right, and 1 meaning 1 tetrahedral sheet and 1 meaning 1 octahedral sheet. So look at this top layer right here. What are those made up of?
Oxygen?
What shape is this?
A triangle?
Okay, it's a triangle, but we gave it a word, right? How many sides does it have?
Tetrahedron.
Yes, perfect. Okay, so this part up here, this is our tetrahedral layer, so 4-sided shapes. And then Manish, down here, what do we got? What are these shapes?
It looks like octahedron.
Correct. Okay,
Yeah.
so when we've got an arrangement of 1 tetrahedral sheet in association with 1 octahedral sheet, that's a 1-to-1. Okay, and then it just kind of repeats itself after that. So again, here's another tetrahedral sheet, and another octahedral sheet. Now let's look at this right side. This is our 2-to-1 clays. All right. Up here we've got what, Freddie?
The tetrahedron.
Tetrahedron. And in the middle we've got O, which is an
Octahedral.
octahedral. And then on the bottom we've got another tetrahedral. So this is our TOTS example, 2-to-1. Tetrahedral, octahedral, tetrahedral. Let's watch this video. I'm going to have to get out of here for a second and copy this URL down. Pull up my YouTube or internet. Can you see and hear that, you guys?
I could see it. I can't hear it very well.
Okay. Can you hear it, Manish?
Actually, I do. I
You
can.
do? Okay.
That'd just be me. That's
Yeah,
okay.
turn up your volume, man. Okay, here we go. This is quick, so it's not going to take very long. Now, before I get going too far here, you guys notice that this guy has a British accent, right?
Yeah.
We all know that the British are the most bright and intelligent people on earth. So we need to pay attention to what this guy's saying. All right, here we go.
But the volume is quite low.
Volume's really low.
Yeah.
Yeah. Like barely hear.
Yeah, let's see. Wonder if, well, let's do this. In the files, I've got this lecture 11 in files. And so you guys can pull that up and copy the link and watch it on your own time.
Okay.
Okay, but let's just watch it. You don't necessarily have to hear what he's saying. It'll be helpful later, but I want to show you how some of these things shriek and swell. Okay. Okay, so we got a sandy loam on the left, clay loam on the right. Now, using your intelligent brains, which one do you think is going to shrink and swell the most?
The clay one.
Why?
Just because of how much bigger of a particle it is in the sand one.
You're right. Okay. The clay one's going to shrink and swell more. And in this case, it has mostly to do with the type of clay in here. All right. So you could, this has got way more clay and it's got a type of clay that shrinks and swells. And in here, we've got much less clay. So watch what happens. They're gonna dump some water in here. And this is pretty exciting. Okay, here comes the water. Did you hear that last part?
No.
Okay. When you watch it, listen, he says that the reason this thing expands is because of hydration within the clay mineral lattice. All right. And we know what that is, right? That's that structure, the sheet-like structure. And hydration means that water can get in there. So basically, water gets into that clay lattice, causes it to expand, and that's why we get this swelling. Whereas this one, it doesn't have the same mineralogy and therefore it doesn't expand as much. All right, let's go back here. Okay. Come on. Can you see that okay?
I can't see it.
You can't or can?
No.
I can't.
Okay, all right. This thing, I don't know why it doesn't like. Now you can?
Yeah.
All right. All right, this is an important subject. Let me swap the display here. This principle of isomorphic substitution or isomorphous substitution is really foundational in soil science. So I want you guys to really understand this. Basically, what happens is I just told you a minute ago that in a tetrahedra, the building block of that is a silicon surrounded by 4 oxygens, right? Well, that is true, but so from time to time, we'll get an aluminum that can replace that silicon in that same structure. Okay. But what's the difference between these two? Look at the charge. What's the difference?
Well, one of them has more.
Yeah.
Plus
Yeah.
one.
So we're going from a system where we've got a +4 charge to a system now where we've got a +3 charge. And so what ends up happening is where we're perfectly balanced before with one silicon surrounded by 4 oxygens. Now we've got an aluminum that's surrounded by 4 oxygens. And the result of that is our particle now has a negative charge. Okay. Because we went from a +4 to a +3, we end up having a net negative charge. And this is what we call isomorphic substitution. So our shape has stayed the same. That's what the iso means. Same form. Okay. But we've gone from a +4 to a +3, and we've got a net negative charge now. Now, the same thing can happen in the octahedral sheet where we get an aluminum that can be replaced with either iron. In this case, when we go from a +3 to a +3, nothing changes except the element. But we could have iron in a 2+ or magnesium in a 2+ that exchanges in that +3. Again, we've got a net negative charge because of that isomorphic substitution. So I know you're going to be asked this on a test or a quiz in the near future. When I ask you to describe what isomorphic substitution is, basically the answer is it's when an element that has a lower charge substitutes for another element that has a higher charge. And the result of that is that the particle becomes negatively charged 99.9% of the time. Okay. Does that make sense, you guys?
Yes.
Okay. Now, I talked about how the soil is reactive. The reason it's reactive is because this happens. So we've got this net negative charge now. And so the soil can react with other things that are charged. And they're usually positively charged, right? You guys remember that opposites attract? And so if we've got a negatively charged clay particle, the things that are going to attract to that are usually positively charged. Okay. Have I beat that one to death yet? Let's use this same figures here and look at how this might happen. Okay. Does this look familiar?
Yeah.
So we've got our silicon right here surrounded by our 4 oxygens. Another one's come in. But wait a minute. Uh-oh, look at that. Now we've got an aluminum in there. So this is +4. This is +4. This is a +3. Okay. So our shape is the same, but now, because this is only a 3 and not a 4, we end up having a negative charge out here, right out here. Sound good?
Yeah.
Let's do the same thing with an octahedron, okay? So aluminum surrounded by oxygen, shapes. Now, wait a minute. It's that purple guy. That's like a magnesium or something. It's only a 2+. Okay. So we've kept our same shape. Our charge is different now. Oh, there's another one. So in this case, we've substituted 2 of these guys in. So we'd have a negative charge here and a negative charge out here. Ah, super. Man, this is so fascinating. I wonder how they figured this out, right?
Yeah.
Must have been some genius. It wasn't me. All right. Now we need to talk about really quickly this idea of charge imbalance. Now, I just told you, right, that we can have negative charges here, negative charges here. And if we go back, we can have a negative charge here.
Yeah.
But I'm here to tell you right now that in nature, these charges that get left end up being occupied by something. Okay, so probably we'll have like a hydrogen. I can't draw. Let me draw here. Hydrogen's positively charged, right? It's a +1. So we'll get a hydrogen that'll come in here and it'll occupy that negative charge. Same thing over here. Since we've got -2 charges here, we can actually get something like, well, they're not side by side, but we can get a hydrogen right here and a hydrogen right here. If these things were side by side, right? Like if this was a purple one and this was a purple one, we could have a calcium that comes in here, which is a 2+. And it occupies that negative charge and that negative charge. What I'm here to tell you guys is that in nature, all this stuff balances out. Okay. I told you that soils can have a net negative charge, which is true, but it's not like we've got these electrostatic soils running around. Those charges end up getting balanced out by things that come in and make associations with it. This is an electrostatic association right here. This would be an electrostatic association. So charges get balanced out is what I'm trying to say. All right. That is all I've got for today. We're going to pick it up tomorrow and do lecture 12.1, and we're going to talk a little bit more about properties of colloids. Any questions before I let you guys go?
Yeah. Well,
Yeah.
for the extra credit question on the lab, where was the guy from?
Utah.
I was off.
There were, I think 2 students got it right.
Yeah. Okay.
Yeah. It's funny. My grandpa came from Utah and he talked just that same way. So that was funny. I didn't ding you if you got it wrong, but if there were a few that got it right. And so anyway, it was pretty fun.
All right.
Okay. I'm going to shut the recording off and we'll see you guys tomorrow.
All right. See ya.
See ya.